Hey guys, my name is IBM and a lot of my friends have been asking me to solve 97025 Feb March 2024. This is a planning, analysis and evaluation. The paper has been attached in the video description. The link is in the video description. This is Feb March component 5.2. So these solutions are not final, they are just guiding solutions. You could be able to get better solutions if possible, but I try my level best to make them very interesting and simpler. So without wasting time, I would like to take you to the question paper so that I start solving it. So this is the question paper. It is paper 5, planning, analysis and evaluation. The paper is 1 hour and 15 minutes. I'll try my level best to keep the time. But I may take more time because I'm going to plot a graph, drawing error bars, drawing line of best fit. It is very hard on a computer. So the paper is 30 marks. I'll just go straight to question number 1. This is just a sketch. I'll write the final. I normally write the final solution in the space provided on this page. Even you in the exam on this page, you just draw a skeleton of what you will do. So as you're reading through the question, you are thinking about the instrument, how you'll measure the quantity, how you'll improve the measurement, and how you'll ensure that the measurement is reliable, and which quantities you are going to make to keep constant so that they don't affect the results. So the figure shows a thin cylindrical metal rod of length L. So when I see length L and I see L is big enough, I know that I'll use a meter ruler. That's one. One end of the rod is hit with the hammer. Let's say it is this end which has been hit. I may just sketch here something like a hammer. One end is hit with a hammer. A stationary sound wave is formed, is set up within the rod. The rod vibrates at a resonant frequency F. So I must measure F. So what comes into your mind when it comes to measuring F? The first thing to come into your mind should be a CRO, a calibrated CRO to measure F. Now it is hard for you to change F with a CRO, but it is easier for you to change L by choosing a rod of a different length. So it gives me an impression as if L will be the independent that I will change as the experimenter. And by changing L, I expect F to be different. So F is going to be the dependent variable. A microphone placed at the other end. So we expect a microphone this end. You have two ways of doing this. If you don't know the symbol for a microphone, you can just do this a shape for microphone. And if you don't know the symbol for a cathode ray oscilloscope, you just draw anything and call it a CRO. My students normally do something like this. But of course, this is not the correct symbol, so you have to call this the CRO. This is not the correct symbol for the microphone, so you have to name it a microphone. But if you're good at science, you know the symbol for a microphone. I think a microphone is like this. Then you connect this to in a circuit which has a CRO. You know the symbol for a CRO. I think the symbol for a CRO is something like this. An oscilloscope is something like that. That would be the easiest here. Then a microphone is placed at the other end, so we shall place the microphone at the other end. Of course, I have to leave some gap so that the vibrating metal does not hit the microphone. And I may want to collect a maximum amount of sound. I may put a cone next to, you could put a cone just next to the rod so that as much sound waves as possible can be collected from the vibrating rod and directed to the microphone. So this is going to be a cone or a conical shape or just a cone. It is not a loudspeaker. Then the frequency of the detected sound is F. Remember how we find f from the CRO? F is equal to 1 over t, but t is equal to the length, that is the horizontal length of one wave. Horizontal length of one wave times, I'm going to write a clear explanation in the space provided. So the horizontal length of one wave times, of course, the time-based setting, that is t. So we now know how to find f. But to get a better value of f, we are going to repeat and get f average. So we are going to repeat for the same length L and get f average. A number of rods of different lengths are available, so we have different values of L. It is suggested that f is related to L by the relationship. So this is we have now identified that f is the dependent variable, f is the dependent variable, and L is the independent variable. So I will change L and obtain f. So I must make, for analysis, remember, I will make the dependent on the vertical, or anything related to the dependent to be on the vertical, and anything related to the independent on the horizontal axis. So I have to make f the subject. So if I try to make f the subject here, I notice that f is equal to the square root of E divided by rho. Remember, rho is the density. So density is mass over volume. So I will need a balance to measure the mass. Then volume is going to be cross-sectional area times length. So I will need area is pi d squared over 4. So I will need the diameter, which is going to be measured using a micrometer screw gauge. So I know that I will measure the diameter, use it to find the area, using the area to find the volume, then find the density from mass over volume, and the density should be the same. So it means this one should be kept constant. It is a control variable. Okay, the density should be the same. So I was making f the subject. F is equal to root of E over 2 over rho divided by 2 times L power of n. Okay, I will take the 2 inside. Of course, when I take the 2 inside, if I take the 2 inside, of course, it must be squared. So this is the same as the root of E divided by, when 2 is squared, it becomes 4, then times 0, then this is divided by L power n. Because L is raised to a power, I'm going to introduce either log or I introduce ln. I normally prefer to introduce ln, so I will say ln of f is equal to ln, because this is going to be division, ln of root E divided by, divided by 4 rho divided by L power n. This is the same as ln of f equals to, when I open this bracket, I will subtract, so it is going to be ln of the root of E divided by 4 rho minus ln of L power n. So this is the same as ln of f equaling to negative n ln of L plus ln of the root of E divided by 4 rho. This is just mathematics. So remember, f was the dependent. F was the dependent variable, so I will plot a graph of ln of f on the y-axis against ln of L, because L was the independent, so I will put on the x-axis. So it means, you notice that the gradient is going to be negative n. If I compare this with y equals to mx plus c, on the y-axis I'm putting ln of f, on the x-axis I'm putting ln of L, so the gradient is negative n, and the y-intercept, will be ln of root of E divided by 4 rho. So to find n will be the negative gradient, and to find E, I'll make E the subject here. So it means I have that if I introduce anti-logarithm, it means that the root of E divided by 4 rho is equal to E power of the y-intercept. Then it means I have to square. So this means E is going to be 4 times rho times E power 2 times the y-intercept. Why is it 2 times? I remove the square root on the other side by squaring both sides. Square this, square the other side. So it becomes 2 times the y-intercept, and here the root cancels out. Okay, so I now know how to find E and N. I'll write the procedures. Of course, I've mentioned which measurements to be taken. The control variable, the density should be constant. How I will analyze data, I will plot a graph of ln of f against ln of L. The gradient is that, the y-intercept is that. Safety precautions, because this is a metal rod, it is a metal rod, so for safety, we must make sure that it doesn't roll off. So we could put a sand tray at the bottom, just in case it rolls off or it falls off. And also we should hit gently so that it doesn't easily fall off. But in case it falls off, we have a sand tray at the bottom. So in my diagram, first of all, I will have to suspend this. I will use maybe elastic bands, and I will have, of course, clamp this on a stand. This is just a rough sketch. So this stand is on a table. Of course, if you want, you can fix this with a G-clamp on a table. And what is missing? These are elastic bands. There's a clamp there. I'm going to draw a better diagram. What is missing here? I'm going to put a sand tray at the bottom here, or a cushion, just in case it rolls off. Yeah, I think that is good enough to go. So I'm now going to draw a better diagram on the next page. But before I draw the better diagram, I know which one is the dependent and which one is the independent. I know which one is to be kept constant, and I now know which measurements are to be taken. So what remains is just now to put this in writing. So I will start by drawing, let me draw the bench. So let this be the bench. Okay, so I will put a sand tray somewhere. So I'm going to call this the bench, and I will call this one the sand tray. This is a safety precaution. Then I'm going to put a stand somewhere here. So let me first draw the clamp. So now I will draw the the metal rod somewhere here. think I do this. This is very long. I need space for. Okay, I'll make the road shorter. And I'm going to support this with elastic bands. This is the clamp. So I want to put a hammer somewhere here, although it may not be necessary, but I want my diagram to be interesting and nice. Okay, so this is going to be the hammer. I don't know whether this is the spelling of hammer. This is going to be the stand. This is going to be the metal rod. The next thing is putting because me I know the symbols. I will just draw the correct symbols for the microphone and for the cathode ray oscilloscope, so that I just make my circuit look easier and simpler. But I said I may need a cone so that I collect as much. So I'll put a cone here. So I'm going to put a microphone here. I'll just draw the correct symbol for a microphone. I'll increase the thickness for this. Then I'll put the CRO here. I think the symbol for CRO is something like this. Yeah, that is a CRO. Now the only challenge is how I'm going to hold the cone here. What should I use to hold the cone? Okay. So all I need is the cone. I'm not interested in that stand. So this is the cone. So this, if you're not sure, this is maybe the symbol for the microphone may not be very clear when I do it like this. I'll first of all raise this upwards. Okay, so this is going to be a calibrated cathode ray oscilloscope, and this is the microphone. So this is a cone. The purpose of the cone is to collect as much sound waves as possible and direct them towards the microphone. So I've just put this to act as maybe this could be a wooden block. Okay, so I think I've tried my level best to include everything needed. I don't think there's anything I've not added here. This diagram is just enough for this experiment to be carried out. I have a sand tray down here on the bench. So I will now just write the essay here. I think for the essay I can reduce the thickness. So the diagram looks like that. The diagram looks like that. I've supported the rod with our elastic bands. You could use strings. One end is where we have the hammer, the other end is where we have the microphone. I think there's an E here. Okay, there's a sand tray here just in case the metal rod rolls off. This is just for safety. Okay, so now I will write the SC in this experiment. Remember we said L was the independent variable and we said F was the dependent variable. So I'll simply say in this experiment, L is the independent variable and F is the dependent. F is the dependent variable. So the quantity which I'm going to ensure that it is kept constant is going to be rho. So I will keep the density rho constant. You will not be credited for saying that rho is the variable, the control variable, not at all. One important thing we need to note is that this experiment will be carried out in a quiet room, because every sound experiment should be carried out in a quiet room. If it is a light experiment, it should be carried out in a dark room. So this experiment, the experiment will be carried or is performed in a quiet room. So to collect and analyze data, I will carry out the following steps. So step number one, it's always good to number your steps because you may want to refer to any step. So step number one, of course, I'm going to measure the length of the rod. So I'll tell the examiner that I will measure the length L of the rod using maybe using a meter rule. Using a meter rule. But of course, if I want to reduce the percentage uncertainty when using a meter rule, then L should be large enough. I'll use a large value of L. This is a continuation. I will use a large value of L. I'll use large value of L to reduce the percentage uncertainty. The percentage uncertainty in L. Okay, then step number two. So the reason as to why we need a large value of L is because we want to reduce the percentage uncertainty in L. Step number two, because I will need the volume, because since I need to find the density, I must also measure the diameter to find the volume, or find the cross-sectional area before I find the volume. So I will measure the diameter. I will measure the diameter. I will measure the diameter of the rod using, if I want a very precise value, I may use a micrometer screw gauge. Because the diameter may not be uniform, I may take measurements at different points along the length of the rod so that I obtain the average diameter. So I will measure the diameter of the rod using a micrometer screw gauge at different points. At different points along the length. along the length of the road and obtain the average diameter. And obtain the average diameter. Okay, so why do I need the diameter? I will have to tell the examiner what the cross section, what the area of the road will be. So I will simply say the area or the cross sectional area of the road. The cross sectional area of the road A is going to be equal to pi d squared divided by 4. Because its diameter and area is pi r squared, so I will measure the diameter of the road. The diameter, let me call it D. Diameter D of the road using a micrometer screw gauge at different points along the length of the road and obtain the average diameter D. The cross sectional area of the road A is going to be equal to pi d squared over 4, and the volume is going to be now cross sectional area times the length L. So the volume is going to be A times L. Okay, so which other measurement is remaining? Of course, I need, since I want to find the density, I have the volume now, I need the mass. So step number 3, I will measure the mass of the road. Of course, to measure the mass, you need the balance. Let's say it is a top pan balance. So I'll measure the mass of the road using a top pan balance and determine the density from, of course, density is going to be equal to the mass, which I've measured using a balance, divided by the volume, which I've also obtained from cross-sectional area times L. Then step number 4, of course, I'm now going to assemble the apparatus as shown in the diagram. I will assemble the apparatus as shown in the diagram. I'll assemble the apparatus as shown in the diagram, and the next thing is going to be hit the rod using the hammer, and hit the rod using the hammer. So step 5 is now going to be determining F. Since I've already hit the hammer, the next thing is to determine F. But how do I determine F? First of all, I need find a period. If I find a frequency, and to find the period, I need the horizontal length of one wave on the oscilloscope times the time-based setting. So by noting the horizontal length, of one wave on the oscilloscope, I will determine the period the period T from T equals to horizontal length of one wave times the time-based setting and frequency f is going to be equal to 1 over the period. So f is going to be 1 over the period. Frequency f is 1 over the period. So that is step number 5. Step 6, I'm going to repeat step number 5. I mean step 4 and 5. I will repeat steps 4 and 5. That is for the same value of L. I'm repeating to obtain an average value of F. For the same length and obtain an average value of F. Okay, so I need to obtain an average value of F. For such a measurement involving time, you need an average value. So I need to repeat the experiment to obtain an average value of F. Then step number 7, now this is now just a general repetition for different rods so that I have now several sets of values. So I'll simply say I will repeat the experiment. I will repeat the experiment with different rods or with the rods of different lengths, of different lengths until I have 6 sets. 6 sets of values. Now that I have 6 sets of values, the next thing is now to plot a graph. Step 8, I will plot a graph. We have already seen which graph we are going to plot. So I will plot a graph of, the graph was ln of f against ln of L. So on this graph, if it is a straight line through the origin, if it is a straight line through the origin, no, it's not through the origin, sorry about that. If it is a straight line not, it is not through the origin because it had an x, it has the y-intercept. If it is a straight line not through the origin, then the relationship is valid. If it's a straight line not through the origin, then the relationship is valid. Then we have already seen what the gradient is equal to. So because they told us to how to find n, so we shall just say n is equal to the negative of the gradient. Then we have also just mentioned that E was equal to, I think it was 4 times rho times E power 2 times the y-intercept. That is how we shall find E. Then for what is remaining, this is all analysis. From here, this is analysis of results. Then next is safety. So I will simply say that for safety, So safety precautions for safety. So for safety, I'm going to say heat. No, I will start by placing, I've already mentioned this because I've already placed it on the diagram. You won't be created twice. If you have put on the diagram, it can't be created twice. So I will say place a cushion or sand tray below the road, just in case it falls, and hit gently to prevent the road from falling. Okay, I may want to check how many marking points have I put in this diagram, but I've put so many marking points. So I will use a different color just to give you a picture of how many marking points are here. Number one, I've supported the rod with elastic bands on a stand, and I've put a cone to concentrate the sound waves incident on the microphone. The microphone is and the calibrated cathode ray oscilloscope would give me a mark. This sand tray would give me a mark, but could be created under safety precautions. Saying that L is independent and F is dependent, that is a mark. Saying that we'll keep rho constant, that is correct, to give a mark. Saying that I'll perform the experiment in a quiet room because it is a sound experiment, it must be performed in a quiet room. Then I'll measure the length L of the rod using a meter rule, that is correct, one mark. Using L as large as possible, that is a marking point. I'll measure the diameter using a micrometer screw gauge, that is a marking point. Then saying that I'll measure different points along the length of the rod and obtain an average diameter. You are improving the measurement, that is a point. Then you are telling the examiner how you find the cross-sectional area and the volume. The examiner could credit you at this point, but that point could be credited here. You will measure the mass we'll measure the mass of the rod using a top pan balance and determine the density from that expression. Then I'll assemble the apparatus as shown in the diagram and hit the rod using the hammer. Then by noting the horizontal length of one wave on the oscilloscope, I will determine the period. You will determine the period from t is equal to the horizontal length of one wave times the time base setting, that's a mark, and f is equal to that. Then you repeat steps to get the average value of f, that is a point. Then you repeat the experiment to get different values. The graph to be plotted, that is a point. It is a straight line but does not go through the origin. That is a point. Then stating what n is equal to e and what n is equal to and what e is equal to, that is a point. Then safety precaution, that would be another point. So I've given more than 15 marking points. You can't fail to write 15 because the examiner will look for 15 important points. I think that marks the end of question number 1. We should go to question number 2. The student investigates an electrical circuit. A power supply with negligible internal resistance is connected to 6 resistors, each of resistance Z and a resistor of resistance R as shown. So that is the diagram. The current measured by the ammeter is I. The experiment is repeated for different values of R. It is suggested that I and R are rated by this equation. You just look at this point here, which graph is to be plotted. Whichever is on the y-axis or anything related to what is on the y-axis should be made the subject. So from that equation, I will first of all divide by I both sides. So I have E divided by I is equal to 3R plus 4Z. I've divided both sides by I. Then it means 1 over I is equal to, I'm dividing both sides by E. So this is going to be 3 over E times R plus 4Z over E. So I'm going to compare this with y equals to mx plus c. That is the equation of a straight line. Y equals to mx plus c. On the y-axis, we have 1 over I. On the x-axis, we have plotted r. So it means the gradient is 3 over e. So this will be 3 divided by e. Then the y-intercept, see, this is the y-intercept. So the y-intercept is going to be 4z divided by e. Values of r and I are given in the table. Okay. Calculate and record the values of 1 over I. Include the absolute uncertainties in 1 over I. So I'm going to maintain the same number of significant figures, or you can increase or maintain the same number of significant figures. So I have 1 divided by 225. Oh, there's a power of minus 6 here, which is not here. So I'll repeat this. 1 divided by 225. Let me put this in brackets. 225 exponent minus 6. So that is 4444.4 recurring. So I'll write 3 significant figures. So I'll write 4440 plus or minus. You can write 44444. The next one is going to be 1 divided by 185 exponent minus 6. So this is 5410. 5410 plus or minus. Those are 3 significant figures. 1 divided by 160 exponent minus 6. So this is 6250. Then we have 1 divided by 140 exponent minus 6. So that is 7140. 7140. The last 0 is because I'm rounding off to 3 significant figures. Now this is the challenge. 1 divided by 125 exponent minus 6. This is 8,000. Because these zeros are not as a result of rounding off, it means they are all significant. So more significant figures are allowed, but not less than 3. The last one is 1 divided by 115 exponent minus 6. So this is 8696 or 8700. 8700 plus or minus. Now this appears as if I've reduced the number of significant figures, but note that this was 8695.6 or 0.7. Now if I try to round off to 3 significant figures, when I try to make this one 0, this automatically also becomes 0, making this one to be 7. So there is no any other option here apart from that one, or you write this, the whole of this, 8696. But I'll write 8700 for easy plotting. Okay, then the uncertainties. Remember the uncertainties in a reciprocal. I've recorded many papers about this. If I have I and I want the uncertainty, absolute uncertainty in 1 over I is the same as absolute in I divided by I times 1 over I. For example, for the first one, absolute in I for the first row, it is going to be 5 divided by 225. I don't need to add the power because it cancels out. Then times 4440. 5 divided by 225 times 4440. This is approximately, when you round off to one significant figure, this is 99, but one significant figure, it will be 100. So I'll just write this is the same as 98.7 or approximately 99. You can write 99, but I want one significant figure, which is 100. So this will be plus or minus 100. The next one will be 5 divided by 185, then times 5410. So I'll write one significant figure, which will be, or I can even write two significant figures. The mixture is allowed. So this will be 150. This is approximately 150. The next one is going to be 5 divided by 160 times 6250. So this is 195, which is approximately 200. The next one is 5 divided by 140, then times 7140. That is 255, which is approximately 260. You can write 300, it is allowed, but I will just write 260. The next one is 5 divided by 125 times 8,000. That is 320. And the last one is 5 divided by 115 times 8700. So this is 378, which is either 380 or 400. I will just write 380. You could write 400. So I could write all these uncertainties as 100. I write this as 200. I write this as 200. I could write this as 300. 300. I could write this as 400. That would be still acceptable. Then plotting the graph, I'll have to write these values on paper so that plotting becomes very quick for me. Okay, so now it's now time for plotting. So remember, I will find the gradient of the best fit. I'll find a gradient of the worst fit. Then for the uncertainty, I'll subtract the two. So let's first plot. To easily plot this, I'll rotate the graph so that I have a bigger space for easily plotting. Okay, so I'm plotting a graph of 1 over I against R. It means the error bars are going to be on the vertical. So for R equals to 1.25, on the x-axis, the scale is 1 divided by 10, which is 0.1, I think. So 1, 2, 3, 4, 5. This is, no, that is 2.5. This is 1.1, 1.2, 25 is in between here. This is plotted against 4440. On the vertical, the scale is 500 divided by, I think it's 500 divided by 10, which is 50. On the vertical, it is 500 divided by 10, which is 50. So 450, this is 40, 4050, 4100, 4200, 250. Okay, this is 300, 400. So 440 could be somewhere in between here. So I'll just take approximately this point here. It's almost to the next line around there, but it's in the middle of this box. Okay, the next point is, of course, when you are plotting, you should be very careful so that your point looks extremely neat. Okay, the next point is 2.55, 2.1, 2, 3, 4, 5. Then 5 is in the middle of the box, 2.55. It's plotted against 5410. So this is 500, 50, 100, 200, 300, 400, and 10. So it is around here. It is around there in the middle of the box. The next is 390, 3.9, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. It's against 600, 6,250. So 600 and 6,100, 200, 250. I think it is here. So this is exactly here. Then the next one is 5.25 is against 7,140. So 5.25 is in 5.1.25 is in here. It's against 700, 7,100. This is 140, must be in between here, almost on 150. Then the next point is 6.55. 6.55 is against 800. I think that is the easiest. 6.1, 0.2, 0.3, 0.4, 0.5. 55 is in the middle here. Then the next point was 7.8 against 8,700. So 7.8, I'll count 8 boxes. Then against 8,700, this is 8,500, 8,600, 8,700, 1, 2, 3, 4, 5, 6, 7, 8. So this must be here. And when you look at my points, they must be showing an almost straight line. So now next is to draw the line of best fit, but I can first draw the error bars. For the first line, the error bar was 100. Okay, so I'll slightly increase the thickness for the error bars. So 100, remember on the vertical, each box is 50. So 100 means those are 2 boxes. So I'll say 100 at the bottom. Those are 2 boxes below. And then 2 boxes above, 1, 2. Then we draw the vertical line through. This must be done using a ruler. The next one is 150. So those are 3 boxes below and 3 boxes above. So 3 boxes below, 1, 2, 3 here. Then here. When you use a sharp pencil, you just pass your pencil there twice and make it look very beautiful. Then you draw the vertical line. This is, I think, in the middle of the box. The next one is 200. Those are 4 boxes above and below. So 1, 2, 3, 4. Then 1, 2, 3, 4. You're not supposed to use a free hand for these error bars. You use a ruler to make them look very neat and beautiful. And I said you pass there the pencil twice so that they look thicker and nice. Then the next one is 260. So those are almost 5, slightly above 5 boxes. So we have 1, 2, 3, 4, 5, slightly above. 1, 2, 3, 4, 5, slightly, because it's 260. The next one is 320. Those are 6 boxes, 6, almost 6.5 boxes. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I slightly stretch beyond 6 boxes, slightly, because it's 320. I don't want to reach the center because it's not 25. Then the next one and the last one is 380. If you want, you could have plotted, if I had plotted one significant figure, it would be very easy. So the next one is 380, which are, those are 6, 7 boxes and a half, slightly more than half. So 1, 2, 3, 4, 5, 6, that is 300, 350. And I will say 350, almost past half. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7 and a half, almost 7.5. So this is going to be here. Okay, so you should draw better error bars than mine. Next, I will draw the line of best fit. I'll just use the same color for the line of best fit. So, of course, for the line of best fit, it goes through the plotted points, but try to balance the plotted points to ensure that the line cannot be rotated any further. Okay, I'm just going to choose this to be my line of best fit. You can draw a better one. I've chosen this line because it is leaving 1 point above and 1 point below. So I'll call this line of best fit. Then I'll draw the line of worst fit. I'll change the color. Even in an exam, for the worst fit, it is just a single judgment. So you can use a pen because you're allowed to have a pen. You can use a pen for the line of worst fit, but that is if you have made the correct judgment. Because if you make a mistake and you want to change the line, then it will look weird, it will look lousy. So I can join the top of the top error bar to the bottom of the bottom error bar as long as all the error bars are crossed. Or I can join the bottom of the top error bar to the top of the bottom error bar as long as all the error bars are crossed. So if I join the bottom, one of them will not be easily well crossed. So I'll check the top. If I check the top, from this top, it crosses this one, it crosses this one, it crosses here, it crosses here, up to here. So I think this can work. So it should the farthest it should cross is this point here. So that's what we mean by it crossing all the error bars. So this is going to be my line of worst fit. Then I'm going to choose points for the gradient. I'll just choose the same point. I will check and see if there are points which can give me the same triangle. For example, I have this point here. Okay, I have these 2 points. I will approximately take this point and this one here for the triangle. Then at the top, I'll look for 2 points, very beautiful points for the triangle. For example, this one and this one. So I will draw my triangle through these points. Make sure your triangle is neat and visible. You can use a sharp pencil. So that is the triangle for the gradient. So for simplicity, I'm going to write out the points that I'm going to use so that I save time. So for the best fit, I'll just read from directly. Note that this is best fit. I don't want to write because when I write it is going to turn, but let me just turn the graph so that I just go back to its original position. Okay. So I have to take readings for the best fit. So for the best fit, I will have the y values. Then for the worst fit, I'll also have the x and y values here. So let me just read them here. So from here, for best fit, blue is best fit. The x value is the x value for blue. I aimed at this point here, which is 2.1. But of course, that is x1. So that is 2.1. Then for the other one, for the worst fit, I aimed at this point here, which is 2.2. Then the y1 values, the y1 values are the same. So this is 5,000. This is also 5,000. Then I'll check. Here the x value is the same again, and the x value for this x2 value is the same here, which is this value here. 7.123456 7.6. So x2 here was 7.6 and here it is also 7.6. The y values are the ones which are different. So I'll read the y values here. For best fit, it is 1, 2, 3, 4. 4 times 50, that is 200. So that is 8,900 for best fit. It's 8,900. Then for the worst fit, I aimed at this point. Make sure you choose a point where the grid lines cross. I was aiming at such points where the grid lines cross. So this is this point here, which is 9,000 minus 100. I hope I didn't make a mistake here. 50, 100, 200. This is 700, it's not 900. The scale on the vertical is 500 by 10, which is 50 for one box. So this was 100, 200, which makes it 8,700. Then this is 8,800, 8,900. So the other one is 8,900. 8,900. I hope I read the values correctly. Remember, these are just guiding values, so you can be very careful when you're carrying out this. So I'll just transfer this on paper so that I just transfer it in the space provided. So one other important thing you need to note from the graphs that I've drawn, you notice that the worst fit is steeper than the best fit. By the way, do not forget to label. This is best fit line, and this one is the worst fit. Of course, when you write the worst fit, the examiner will know that you are referring to worst fit line, so you don't need to write a lot of statements. But make sure you label the lines, otherwise you won't get the mark there. Okay, so I'll now just substitute values, or just write here to find the gradient. For the best fit, we say the change in the y values, we have 8,700 minus 5,000 divided by 7.6 minus 2.1. For the worst, we had 8,900 minus 5,000 divided by 7.6 minus 2.2. Also, you should be able to check if there is a power of 10. For example, here it is on the vertical it is amperes per ampere, and on the horizontal it is kilo. You must be careful with that. It is kilo here, it is kilo ohms. So when you're finding the units in the next page, you may be very careful with that. For now, I will not add it here because I may use kilo in the next part. So this is going to be 8,700 minus 5,000 divided by 7.6 minus 2.1. So this is giving me 672.7. I'll just round off this to 673. Of course, the units are not asked, but you can check them. On the vertical, it was per ampere. On the horizontal, it was kilo ohms. Remember that. Then here, 8,900 minus 5,000 divided by 7.6 minus 2.2. We expect this to be steeper, so this is 722. So the gradient here is going to be 673 plus or minus. The uncertainty we shall subtract. 722 minus 673. 722 minus 673. So this is approximately 49. Okay. Determine the y-intercept of the line of best fit. Include the absolute uncertainty in your answer. Now, you don't read the y-intercept from the graph. You use the equation y equals to mx plus c, which means c is going to be equal to the y value minus m times x. So because they want us to include the absolute uncertainty, the easiest method is to find c for the best fit and C for the worst fit, and maybe subtract them. So I'll find C for the best fit, which means I'll use the best fit values. I'll take a pair. Let me take this pair here for the best fit value. The Y value is going to be 8,700 minus the gradient of best fit is 673, I think. 673, then times the X value, which is 7.6. So this is times 7.6. Then for the worst fit, C worst fit is going to be the Y value. For the worst fit, I will take this pair of values. So this is going to be 8,900 minus the gradient was 722 for the worst fit times the X value, which is 7.6. So I have 8,700 minus 673 times 7.6. So this is giving me 3585. And this one is giving me 8,900 minus open brackets 7.6. So 7.6 times 722. So this is giving me 3413. 3413. Then the uncertainty is the difference. Is going to be 3585 minus 3413. Don't mind about the biggest, you just want the difference. So it is always highest minus lowest. After all, the uncertainty is plus or minus. So I have 3585 minus 3413. So this is 172. So it means the y-intercept is going to be the best fit value, which is 3585 plus or minus 172. Use your answers to A, C Roman 3 and C Roman 4. Determine the values of E and Z. Okay. Remember we said the gradient was equal to 3 divided by E, which means E is going to be 3 divided by the gradient. They said include the appropriate unit. So this is going to be 3 divided by the gradient, which gradient was 673, I think, for the best fit. Then we also saw that the y-intercept was equal to 4z, I think, divided by E, which means z is equal to E times the y-intercept, and we divide this by 4. Okay, so this one is going to be E. Let me first find the value of E here. 3 divided by 673. So this is 4.46 times 10 to the power of minus 3. 4.46 times 10 to the power of minus 3. This is, remember the gradient was, this is the gradient had units which were per ampere divided by kilo ohms. When this goes up, it becomes gradient is at the bottom. So this is, remember this was per ampere per kilo ohm. I want to remove the kilo here, so I'll say times 10 to the power of, let me see where the kilo will be here on the gradient. The denominator is the one which was times 10 to the power of 3. The denominator is this, the one which was times 10 to the power of 3. So when I get the reciprocal, the power of 3 goes up. So this goes up. So times 10 to the power of 3. When I get the reciprocal, so this is the same as kilo ohms divided by per ampere. And the kilo is power 3. Let me just remove this. Because the gradient is at the denominator, so it is kilo ohms per ampere. And note that kilo is power 3. So this is going to be kilo ohms amperes. Okay. So the units can be kilo ohms amperes, or you can write 4.46 ohm amperes instead of kilo ohm amperes. So this is the unit here. Then for Z, I'll substitute Z, as Z is going to be, when I put in the values for Z, Z is going to be E, which is going to be 4. I'll just remove the kilo, so that is 4.46 ohm amperes times the y-intercept. The y-intercept is going to be the best value, which I have as 3585. So this is 3585, and this is per ampere, that is on the y-axis. Then I divide this by 4. So 4.46 times 3585, divide this by 4. So this is giving me 3 approximately 4.0. So I'll just write 4.0 times 10 to the power of, this is power of 1, 2, 3. So this is power of 3, and this is going to be ohms. Because I removed the kilo, so that is going to be ohms. Okay. So it is 4.0 times 10 to the power of 3 ohms. Okay. So you could get values which are around these ones that I've got, or values which are slightly different from these ones. And of course, by the way, I think ohm amperes is the same as resistance times current, that is volts. So this could also be 4.46 volts. I think so. Okay, so I think could be Z could be something like that. Then determine the percentage uncertainty in Z. So note that Z is equal to that. So I will say percentage in Z is going to be percentage in E plus the percentage in the y-intercept. So this is going to be the percentage in E is going to be the absolute in E. Do I have absolute in E? I have the absolute in the y-intercept, the absolute in E. So for absolute in E, I'm going to be forced to find the absolute uncertainty in E is going to be equal to, of course, it is going to be the same as, because it is E is E3 over the gradient, so it is going to be equal to the absolute of in the gradient divided by the gradient times the value of E, that is the absolute in E, which is equal to the absolute in the gradient, which was 49 over 673. So this is 49 over 673 times the value of E, which I got here as 4.46. That is the absolute in the gradient. Or if I want a percentage, why did I bring the 4.6? If I want a percentage, I'll just do this. absolute in E over E, then this side times 100, then this side will be times 100. So this times 100 to make it percentage. So the percentage in Z is going to be equal to 449 over 673 times 100% plus the percentage in the y-intercept. The absolute in the y-intercept is 172. 172 over the y-intercept, which is 3585. Then I multiply this by 100. So I'll just press my calculator. 49 times 100 divide by 673 plus 17200 divide by 3585. So that is 12%. So this is going to be 12% approximately. You could also use another method where you can find, you get Z. You have the Z value here, which was, this is the Z for exact value, 4.0 times 10 to the power of 3. Then you can get Z maximum. Maybe Z maximum, where you'll use E maximum. You'll need the maximum value of E plus the maximum value of the Y times the maximum value of the y-intercept divided by 4. So this would be E max times y-intercept maximum. But this may take a longer method. Then you subtract. The absolute in Z will be the difference. You just get the difference between these two values. But it means it will take you more time to find E, the maximum value of E, which means you'll use the gradient, the biggest gradient. Of course, it's also not a very, you'll use the smallest gradient. So you'll subtract the uncertainty of the gradient from the gradient here, because you want, if E is maximum, then the gradient should be the minimum. So you'll subtract the uncertainty for the gradient to use the smallest value of the gradient here. Then you subtract to find uncertainty in Z. But this one is a direct method if you're good at AS physics. The experiment is repeated. Determine the resistance R that gives a value of I of 0.10 milliamperes. So I'm using E equals to, I think it was 3IR plus, was it 4IZ? We got that 1 over I was equal to 3 over E times R plus 4Z over E. Remember, this was the gradient, the other one was the y-intercept. So 1 over I is equal to the gradient times R plus the y-intercept. So I'm just going to substitute the values here. 1 over I is going to be 1 divided by 0.1 times 10 to the power of minus 3. Should be equal to the gradient, which was 673. The gradient was 673. Then times R plus the y-intercept. I think the y-intercept was 100 and, no, it's 3585. The y-intercept is 3585. Okay. So remember, the gradient, I didn't change the gradient, so you must be very careful with that. The gradient was per ampere divided by kilo ohms, which is ampere. I have to divide this by 1,000, so this would have been times 10 to the power of minus 3, because this is in ohms. Okay. So I want to make the subject here. Making R the subject, I'll just press my calculator. I have in brackets 1 divided by 0.1 exponent minus 3. Then minus 3585. Then divide by 6, 7, 3 exponent minus 3. So I'm finding R as 9531. R is equal to 9531 ohms. That is my value of R. It's because I had to change this from because the gradient, if I try to change the gradient, the units for the gradient, it is 673 times 10 to the power of minus 3. So that gives me 9531. Okay, so if you want, you could have changed the units for the gradient here from this stage here times 10 to the power of minus 3. You could change it from that point, and of course that value would affect this, but I think the units will not affect much here. But of course, in the final value here, when I change this from milliamperes, it means I should also make the units of gradients to be standard, so that my answer comes to this. So R is going to be that. I think I've tried my level best. In case of anything which is not clear, I can always try my level best to give more light. Until next time, bye bye.